video, I would like to do a rundown of what everything is in the AP statistics formula sheet. So it has been updated in 2020, so I have printed out the most updated AP formula sheet. There's also tables included. You get your Z table, you get your T table, and you get your chi-square distributions. I'm not going to talk about the tables, they're pretty straightforward. But instead, what I want to do is I just want to talk through what all available or what all is available to you in the AP formula sheet. What I found in my students in the past is, I mean, the AP formula sheet's great. It's kind of there not as a primary guide. I feel like a lot of my personal students kind of know a lot of what they need, what they don't need. What I kind of more use it as is if I get a very, very tricky problem that I kind of know a bit on what's going on, but I'm stuck. Sometimes formulas and stuff like that will bail you out, okay? Or it asks about those super specific details that, maybe you don't remember what the expected value of a binomial variable is, then you can run to the formula sheet and sometimes it can help you out. Anyways, let's get to it. I want to just run through quickly kind of what different things are in the AP formula sheet. The second page is a lot more helpful. I think it helps you with all of your inference stuff, so your confidence intervals and your standardized tests, your hypothesis testing. So I'm going to fly through this first page so I don't make this video super, super long, and then really focus on the second page of this AP formula sheet because I feel like that's most referenced. So let's get to it. It starts off with some descriptive statistics, and there's 6 kind of pieces here. The first thing it's going to give you is it's going to give you an X bar, which is just simply a sample mean, which most people can do an average. They do a sample mean, but that's on there. Additionally, over here to the side is if you have a sample that you want to find a standard deviation of, they have the formula to find a sample standard deviation. So if they ever ask about that, you're set. The next four are all for your linear regression. Okay, they're all for your linear regression, your line of best fit. So the general equation for the line of a best fit or your linear regression is right here. So that is your equation of the line right there. Y hat equals A plus BX, where A is your y-intercept, B is your slope. Right below it, we have R, which that is the equation to calculate your correlation coefficient, which is nice. In my class, a lot of us, we calculated this by the calculator anyway, so be it. Over here to the bottom right, we have B equals R, standard deviation of Y divided by the standard deviation of X. This is your equation. If you ever had to calculate the slope by hand of your linear regression, that is the equation for the slope. And right above it is, I've seen it more rearranged differently, so I think it's interesting the arrangement that they have. But we have Y bar equals A plus B times X bars. So your average of Y, your average of X. Typically what this equation is used for is you could rearrange and solve for A, and you could solve and get your y-intercept if you so desire. So if you get an average of Y, you have an average of X, and you know the slope, you could plug in and solve for A there is how I use that. The next section, section 2, goes into your probabilities and your distributions. So we got our kind of basic probability function. This is for 2 events A and B that overlap. Great. You have a conditional probability here, the probability of A given B. For my particular classes that I teach, we aren't super, super dependent on these. We kind of work through it our own way. But if you ever got stuck where you're like, I have 2 events that are overlapping, how do I calculate the probabilities? So there's the probability of A or B is the probability of A plus probability of B. Subtract off the probability of A and B. Conditional probability there. Probability of A and B divided by the probability of B. This next section I think can be extremely useful, but I feel like the reason this is missed on the AP exam is sometimes they're hard problems to spot and figure out what they are. So we have a discrete random variable X. That's our probability distribution. A discrete random variable X. You could calculate the mean of it, and you could calculate the standard deviation of it. So click here on a post-it note. Here's what I mean by a discrete random variable. You have some random variable X, has to be discrete. Say it has values 1, 2, and 3. The value 1 has a 30% chance of happening. Value of 2 has a probability of 0.6. Value of 3 has a probability of 0.1. So we have the expected value to find the mean of it. As your refresher, you take X times P plus it to the next one, x times p, add it to the next one, x times p. You do that, you get your expected value. Standard deviation, what you're going to do is take the square root of the sum of x minus mu x squared times px. So this is take your x value, so say it's 1, subtract off your expected value, square it times p. Go to the next one. Take your x value, subtract off your expected value, your ex, square it times p. Go to the next one. Take your value, subtract off the expected value, square it times p. That's what these two are. So that discrete random variable can be tough to see. Next, we have binomial distributions and we have geometric distributions. So if you wanted to find the expected value of a binomial distribution and its standard deviation, you want to find the expected value of a geometric distribution and its standard deviation, you can do that. So some people are like, well, wait a second, what's binomial and geometric? Binomial, a quick example of that is, say you're doing 5 trials of something. You're looking for, say, 2 successes out of 5. So you have a set number of trials, you have a set amount of success, the whole Bernoulli thing. You know, I could talk forever about this. 2 successes out of 5, 3 successes out of 5, et cetera, okay? That's a binomial setup. That's your expected value, that's your standard deviation. Geometric is all about your first success. You know, I'm gonna keep doing something over and over and over and over again till I hit my first success. That is a geometric setup, okay? So you could find its expected value, you could find its standard deviation. Then the AP formula sheet really jumps in and kind of opens up a lot of things here. It's gonna get into your sampling distributions and inferential statistics. Remember, sampling distributions, that's like your collection of p-hats. So maybe I go out and get a sample. I find that sample's x bar. Add it to the stack. Go out and get another sample, same size, but different sample. Get its x bar, add it onto the stack. Sample, x bar, add it to the stack. Sample, x bar, add it to the stack. That collection of all of those x bars, all those sample means, is a sampling distribution. And we have various sampling distributions. That's a basic premise there. Using the idea of sampling distributions, that opens up the world of inferential statistics. So your hypothesis tests and your confidence intervals. So on this next page, there is just a lot. There is a lot there. If you don't know what you're looking for, you can easily get lost. So what I'm going to talk through is all the different intervals and all the different hypothesis tests, how you can use this to come up with those formulas, because they give you a lot of it, but they don't give you everything all the time. So they break it down by talking about your sampling distributions for proportions. So if your problem's dealing with proportions, you got your 1 population, so single proportion, and then 2 populations. So a p-hat 1 and a p-hat 2, you got that stuff. For means, you're pulling from 1 population, so a single x bar. You're pulling from 2 populations, so an x bar 1 and x bar 2. And then we have our sampling distributions for our simple linear regression. That's your confidence intervals and your hypothesis testing that has to deal with the slopes. Okay, that has to do with the slopes. So let's get to it. I kind of want to move through it fast, but if I go too fast, pause me. So what they're always going to tell you is for a confidence interval, it's your statistic. That's your like x bars, your p-hats, plus or minus your critical values. That's your z stars or t stars, times the standard error of the statistic, which they give you the standard error of the sample statistics. So sometimes that's the hardest part of the formula to remember. They give you a lot of that. You just need to know what to pick out. For hypothesis testing, you're going to do your statistic minus your parameter. So maybe your x bar minus your mu. You know, remember statistics are your x bars, your p-hats. Then you have your parameters, which is your mu's, your p's, etc. Okay, and then you're going to divide by the standard error of the statistic. Again, standard error of the statistic, that is the hard part. So let's get to it. I'm going to jump back and forth talking about my intervals and then referencing this sheet. So let's start with just in the proportions. Say I wanted to do a 1 proportion z interval. You got to pick your statistic, which we're talking about a p-hat, plus or minus, and we know it's a 1 proportion z interval, so we're going to have a z star, and then we need our standard error of the statistic. Let's say I forget the back end of this, okay? So with a 1 proportion z interval, we don't know p. All we have is the information about p-hat. So if we go to the 1 population, so a single proportion, standard error of the statistic, there it is, okay? Square root of p-hat, 1 minus p-hat divided by n. That is what's going to go here. P-hat, 1 minus p-hat divided by n. There's your one proportion Z interval. For a one proportion Z test, this is kind of a little bit of a unique one with what's going to happen here on this whole page. So this is where you have like a null hypothesis where you have some population proportion P, and there's some sort of hypothesized, hey, here's what P is. So we have a numerical value for P. So if I'm going to do a one proportion Z test, we're going to have Z equals, need our statistic, which if we're dealing with proportions, P hat. We need our parameter, which is P, and we need to divide by the standard error of the statistic. So on our AP formula sheet, you would say, oh, should we be using the square root of P hat, 1 minus P hat divided by N? This is the rare case in which we do not use this, okay? We have knowledge. We have a numerical value for P. So instead of using the P hats and all that, we're going to use something a little bit better. We're going to use that population proportion there. We're going to do the square root of P, 1 minus P divided by N there. That's the one that's a little bit unique in my opinion, that it kind of breaks the mold of what's going on here. Then let's look at two proportion Z intervals. So I'm going to slide it down. I'm basically using all this stuff right here. So there's the sampling distribution of it. You know, the center of your sampling distribution, your standard deviation. The standard error is what was going to be super helpful to us. And it gives us two options here. One time it uses P hat 1 and P hat 2. The other time it uses P hat C's, which is a combined proportions there. It's pooled. So for a two proportion Z interval, since we're doing two proportion for my statistic, you're just going to start with a P hat 1 minus a P hat 2, plus or minus Z star. Then I need my standard error of the statistic. Since I'm comparing two proportions, we're going to use this guy right here, square root of P hat 1 minus, or P hat 1 times 1 minus P hat 1 divided by N1, plus P hat 2, etc., etc. It's all right there. The standard error is all right there. So P hat 1, 1 minus P hat 1 divided by N1, plus P hat 2, 1 minus P hat 2 divided by N2. It's all there for you. When you move to the two proportion Z test, we're going to do for our null hypothesis, we're going to assume P1 is equal to P2, okay? But we don't know actual numbers for this. So it's not special like this where we're going to be like, oh, well then I could use P1, P2. No. We're assuming they're equal, but no numbers are known. And that's going to be important here. This tidbit's going to be important here when we get to it. So we're going to start with Z equals P hat 1 minus P hat 2. So I'm going to deal with my statistics first. Then my parameters, P1 minus P2. For the standard error of the statistic, that's where this formula sheet comes in play. It says when P1 equals P2 is assumed. That's what we're assuming with our null hypothesis, okay? That's what we're assuming with our null hypothesis. We're going to use this, which is a P hat C. It's a pooling of the samples, So my standard error down there is going to switch to P hat C times 1 minus P hat C, and that multiplies to our fractions of 1 over N1. Oops, shouldn't have done too big of that's two separate fractions. I kind of went a little bit overboard there. 1 over N1 plus 1 over, let me separate that, plus 1 over N2, okay? So that gets a pooling of the samples. Neat. Let's move on to our means. So on the AP formula sheet, they give you, hey, you're dealing with a single proportion, or single population, are we dealing with two? If you're dealing with a single population, your sampling distribution is centered, standard deviation. You're comparing two populations, center, standard deviation. They also include the standard error, which is going to be extremely helpful to us when we come up with our intervals and our tests. So for one sample T interval, follow that same formula, statistic plus or minus critical value times the standard error of the statistic, which we might lean on the AP formula sheet there. Standardized test statistics, so for your hypothesis test, statistic minus parameter divided by the standard error of the statistic. So for one sample T interval, we're talking X bar plus or minus T star, and then pool that standard error of the statistic. Standard error of the statistic is S divided by the square root of N. S divided by the square root of N, okay? We don't know sigma, so we're not using this guy. For my next one, for a one sample T test, yeah, we're going to assume mu is equal to some sort of number, but we don't know sigma, and that's going to be important to us as we get through this. We don't know sigma. So we're going to have T equals, start with your statistic and your parameter, X bar minus mu, okay? But here's the deal. We don't know sigma, so we're going to use the standard error here. S divided by the square root of n. S divided by the square root of n. I don't know sigma, so don't even mess with this like you did with the 1 proportion z-test. Then something I teach is paired t-intervals and paired t-tests. Those are the problems that it presents like it's 2 different data sets, but really the data sets are paired and tied together. So you find the difference and you create a single data set. These paired t-intervals and paired t-tests, I've talked about it in my class. They're 1 sample t-intervals and 1 sample t-test in disguise. Okay, they do a great job of presenting themselves as if it's a 2 sample situation, but the individual data points are linked together. So it's very, very simple. I don't want to spend a lot of time on it. We're talking x bar d plus or minus t star, sd over the square root of n. That subscript d is just talking about the differences between our 2 data points. For the paired t-test, we're talking t equals x bar d minus mu d, which is often 0, divided by, I'm kind of crammed in here, s divided by the square root of n. And then finally, we have a 2 sample t-interval and 2 sample t-test. So now we're switching from single populations to 2 populations to a 2 sample t-interval. So start with your statistic, x bar 1 minus x bar 2 plus or minus t star. Then you need your standard error statistic. Check your formula sheet. If we're talking about 2 populations, your standard error is this guy over here. So the square root of s1 squared divided by n1 plus s2 squared divided by n2. That's your 2 sample t interval. 2 sample t test. So this is where you're assuming mu1 is equal to mu2. We still don't know information about sigma. So following what they say for a test statistic minus parameter divided by the standard error. So statistic x bar 1 minus x bar 2. Parameter mu1 minus mu2. We then need our standard error of the statistic, which is, hey, the square root of s2 squared, or sorry, s1 squared over n1, s2 squared over n2. That is all on the bottom. So just like that, I was able to pull together all my proportion, confidence intervals, hypothesis tests, all my means, confidence intervals, and hypothesis tests. Only a few ones left, and then we're going to call it. Chi-squared is really, really nice. For whatever reason, of all the things they give you on the AP formula sheet, chi-squared is the one that they just give you the whole thing. They tell you the chi-squared statistic. There is no confidence interval. They give you the whole thing on the AP formula sheet, so there's really no mystery about it. It's just on there. You're going to take the summation of your observed counts minus your expected counts, square it, and divide by your expected counts. It's on the AP formula sheet. It's nice. The final thing I want to talk about is when we're doing confidence intervals and hypothesis tests for slope. So a t-interval for slope or a t-test for slope. T-intervals for slope or t-test for slope. So for this one, you could take your sample slope, which is B1, that's your statistic, plus or minus t star. And what we need is we need the standard error of our slope. The standard error of our slope, which this is on our AP formula sheet. When you're dealing with slope, the standard error of the slope, there it is, s divided by sx times the square root of n minus 1. So that piece right there is given to us. It's s divided by standard deviation of x times the square root of n minus 1. Oftentimes, these problems are computer printout problems. They kind of give you the standard error already. You just need to know where to look for it. But if you had to calculate it, it's on the AP formula sheet. Finally, your t-test for slope. T-test for slope. So you have to take your statistic, so our sample slope, minus our population parameter. So that's our population slope. That's capital beta there. 1. And then divided by the standard error of B1. Standard error of B1. Again, it's on the AP formula sheet right there. Again, oftentimes, these standard errors, it's a computer printout problem, so they often give you standard error of that slope for you. You just need to know where to look. And I guess one piece I should have added on there is oftentimes there's a hypothesized population slope there that you work with. So there you have it. Whew, long video, but that is everything on the AP formula sheet. There's a lot there. If I went too fast on the part, back it up, rewind it, see what's on there. But there's a lot there, It could really bail yourself out if you need it. So you got, again, sample mean, sample standard deviation, your regression stuff, probabilities, your random variables there, binomial distributions, geometric, and then a whole bunch of stuff to help you with sampling distributions, confidence intervals, and hypothesis tests. I know it's a long video, but hopefully it was informative about what's there. My students, we kind of use the formula sheet as, hey, I'm completely stuck. Can it bail me out? Because a lot of stuff is probably already in your head anyways, but AP formula sheet can help you out when you get in tricky situations. Good luck.